Isn't it funny how some really powerful ideas have these surprisingly unassuming names? Take the Monte Carlo method. It just sounds like something straight out of a casino, right? High stakes gambling.
It totally does. But yeah, behind that sort of glamorous name, it's actually this computational powerhouse.
Yeah.
Really foundational stuff.
Used in everything from, I don't know, designing smarter AI to predicting financial market swings.
Exactly. It's that contrast that's so interesting. A name all about chance, but the method. It gives you incredibly solid estimations for some really, really complex systems.
So today, we're going to peel back those layers, figure out what the Monte Carlo method is really all about.
Yep. Our mission today.
Forget the casinos for a bit. We're talking about a way to tackle really tricky problems by essentially running simulations, just trying things out again and again, but with a bit of randomness each time.
Right. It's like harnessing probability itself to get a grip on uncertainty. So, when a direct formula, that neat step-by-step solution, is just too hard to figure out, or maybe doesn't even exist, that's where Monte Carlo steps in. It sort of embraces the fuzziness, runs tons of simulations, all slightly different, and then looks at the pattern of results.
To get a reliable estimate.
Precisely. It's the go-to for systems that are just, too tangled up for standard math to easily solve.
And for this deep dive, we're looking at a really helpful blog post by Victor Leung. It's called Monte Carlo Method: From Statistics to Smart AI Agents, Continuous Improvement.
Yeah, it's a good one. Lays things out clearly.
So our mission today is to really get the core idea, understand why it's so important everywhere, especially AI, which is fascinating, and maybe find some surprising uses. Basically, your quick guide to understanding this powerful technique.
Sounds good.
Okay, so let's start simple. What is the Monte Carlo method, basically?
Okay, well, at its heart, like Victor Leung's post says, it's really a family of computational methods. They all rely on repeated random sampling, drawing random numbers again and again to get numerical results. The core idea is simulation, running a process, maybe particle physics, maybe stock market moves over and over. And by looking at all those results together, we can make pretty good estimations or predictions.
So running the same thing many times, but each run has that little random twist?
Exactly. And like the blog post stresses, this really shines when getting a direct analytical solution. That nice, clean formula is super hard or just plain impossible.
When things get messy.
Yeah. Think systems with tons of interacting parts or systems that are just inherently unpredictable, maybe even chaotic. That's where Monte Carlo offers this really powerful alternative way forward.
The blog post uses a great example to visualize it. Estimating pi, which seems wild, right? Using randomness to find pi.
It's actually a really clever way to show the principle. It connects geometry to probability. So imagine a square. And inside it, fitting perfectly, is 1/4 of a circle.
Okay, got the picture. Square, quarter circle inside.
Now, imagine you're just randomly throwing points, like darts, at the square. Some land in the quarter circle, some land outside it, but still in the square.
Okay, a whole scatter of random points.
Right. Now, here's the neat part. The ratio of the quarter circle's area to the whole square's area is pi divided by 4. So if you throw a massive number of these random points, the fraction of points that fall inside the quarter circle gets really, really close to that pi-4 ratio.
Okay.
So to estimate pi itself, you just take that fraction you found and multiply it by 4.
Wow.
It's trading complex calculation for just lots of random throws and probability. A surprisingly simple idea, but with really deep implications.
That's incredible. No fancy geometry needed directly, just tons of random points and simple counting. Really intuitive. Okay, so we see what it is. Now, the post stresses its importance in statistics. Why is this such a big deal there?
Well, if you think about that simulation idea, you can immediately see the connection to stats. One huge area is simulating probability distributions. Sometimes the way things are distributed in the real world is super complex. We don't have a neat equation for it. Monte Carlo lets us generate samples that behave like that distribution, even without the equation.
Right, so you can study how it works even if you can't write it down perfectly.
Exactly. It gives us a handle on its characteristics. And, as Leung's post mentions, it's also vital for solving integrals, especially high-dimensional ones.
Integrals, like finding the area under a curve, but more complex.
Yeah, I think finding the volume of some bizarre shape, but not just in 3D, maybe in, 50 dimensions. Traditional calculus methods just break down. Monte Carlo offers a way to sample points within that space and estimate the volume.
High dimensions. Sounds like it gets complicated fast.
Oh, it does. And think about risk analysis and forecasting. That's huge in statistics, right?
Sure, like in finance.
Exactly. You build models with random variables for all the uncertainties, then you run Monte Carlo simulations, thousands of them, to explore the whole range of possible outcomes.
So instead of one prediction, you get a whole cloud of possibilities.
Precisely. You see what might happen and how likely each scenario is. Super valuable for assessing investment risks or project delays, anything with uncertainty.
Like getting thousands of possible weather forecasts instead of just one.
That's a great analogy, yeah. And one more key area the post mentions is Bayesian inference.
Okay, that's about updating beliefs with new data.
Right. A core challenge there is analyzing something called the posterior distribution, your updated belief. It can be mathematically very tricky.
Huh?
Techniques like Markov chain Monte Carlo, MCMC, use these random sampling methods to explore that posterior distribution. It makes Bayesian analysis practical for complex real-world problems, like updating your weather guess based on the clouds you actually see.
Okay, wow. So from estimating pi to being fundamental in stats, it's clearly a major tool. Now, the blog post gets really exciting when it talks about AI. How has this random simulation idea changed artificial intelligence?
Yeah, this is where it gets truly transformative. The impact on AI, especially anywhere involving uncertainty, exploration, making decisions, it's just massive. And Victor Lung's post rightly zeroes in on Monte Carlo Tree Search, or MCTS. That's a key application.
MCTS, got it. What is that exactly? And why is it such a, well, game changer, literally?
It is. MCTS is a specific type of search algorithm for decision-making, hugely influential in games. The core idea is finding the best move by simulating thousands, even millions, of random games, random playouts, starting from the current position.
So the AI is basically playing tons of super fast hypothetical games in its head.
Exactly. And it does this by balancing two crucial things the post highlights: exploration and exploitation.
Exploration and exploitation.
Exploration means trying out moves that haven't been looked at much, even if they don't seem great at first glance. You might discover a hidden gem.
Right, find something new.
Exploitation means sticking with moves that have worked well in past simulations, the tried and true options.
It's like trying a new restaurant versus going to your old favorite.
Perfect analogy.
Right.
You need that balance. You don't want to get stuck in a rut, but you also don't want to waste time on obviously bad ideas.
Makes total sense. So how does MCTS actually work? What are the steps?
The blog post breaks it down neatly into 4 stages. First is selection. You start at the current game state, the root of the tree, and move down to a leaf node using a SMART policy. Like UCT upper confidence bound for trees is a common one. It helps balance that explore-exploit dilemma.
Okay, so it picks a path down the possibility tree. Then what?
Step 2, expansion. Once it hits a leaf node that hasn't been fully explored, it adds a new child node representing a possible next move. Just grows the tree slightly.
Got it.
Third is simulation. From that new node, it runs a random simulation, often called a playout or rollout, all the way to the end of the game. This is usually fast and not very sophisticated, just random moves.
Just see what happens randomly.
Exactly. And the final step, 4, is backpropagation. The result of that random game, win, lose, or draw, is sent back up the path it took through the tree. It updates the stats for all the nodes along that path.
Stats like how many times that move was tried and how often it led to a win.
Precisely. So with every simulation run, the AI learns a tiny bit more about which moves tend to lead to good outcomes.
And over millions of these runs,
The tree gets refined, the better moves get visited more, their win rates go up, and the AI gets a really good idea of the best move to actually play in the real game.
and this is the magic behind DeepMind's AlphaGo beating world Go champions. The post mentions this, and it's still just mind-blowing.
It really is. Go has this absolutely enormous number of possible games. More than atoms in the universe, people say. Traditional AI search just couldn't handle it.
They would get lost.
Totally lost. MCTS, with its smart blend of exploring possibilities and exploiting known good paths, gave AI a way to navigate that complexity without looking at everything. It learned through simulation.
Astonishing. But it's not just games, right? The post mentions broader uses for AI agents, planning.
Oh, definitely. Beyond games, lots of real-world problems AI faces involve uncertainty, missing information. Monte Carlo is great there, too.
Like in reinforcement learning, where AI learns by trial and error.
Yeah, exactly. Monte Carlo methods can estimate the expected long-term reward, the return, by sampling different sequences of actions, different episodes. Again, trying things out virtually to see what pays off.
Even if the AI doesn't perfectly understand its environment.
Especially then. If the AI doesn't have a perfect map or model of the world, Monte Carlo simulations help it evaluate different strategies and figure out which ones work best just by trying them out and observing.
And the blog post mentioned POMDPs. Partially observable Markov decision processes? Sounds complicated.
It's a bit more advanced, yeah.
Yeah.
It deals with situations where the AI can't see the whole picture. It only gets partial clues about the state of the world.
Okay.
So the AI keeps track of its belief about the true state. Monte Carlo simulations are often used here to update those beliefs based on new observations and to plan actions, considering all the possible states the world might be in.
So it's like the AI is running constant what-if scenarios based on its limited view.
That's a really good way to put it, trying to figure out what's likely going on and what to do next.
Fantastic. Okay, before we get totally lost in AI, the blog post does quickly mention other areas. It seems like this method just pops up everywhere.
It's incredibly versatile. Its reach is really wide, like the post notes in physics, simulating super complex particle interactions.
Wow.
In finance, it's a standard tool for valuing complex derivatives or figuring out portfolio risk, understanding the range of potential gains or losses.
From particle physics to Wall Street, quite the range.
Absolutely. And there's robotics. Something called Monte Carlo localization helps robots figure out where they are using probabilities. Even medicine, modeling radiation dose distributions for cancer therapy, for example. It just shows how adaptable the core idea
It
is.
really is amazing. This simple core concept, randomness, repeated trials, just keeps proving useful in so many different places. So wrapping up our deep dive, what are the main takeaways from Victor Leung's post about the Monte Carlo method?
I think the key thing, as the post concludes, is the sheer brilliance in its simplicity and flexibility. It takes randomness, something we often try to avoid, and turns it into a tool.
Right.
A tool to get practical, approximate answers for problems that might be otherwise unsolvable. Its journey, from theoretical stats to driving cutting-edge AI like AlphaGo just highlights its incredible impact.
Absolutely. From figuring out pi with random darts to letting AI master Go, quite a story. And it seems like its relevance is only going to increase as computers get more powerful.
That's a really important point. More computing power means more simulations, which means more accuracy and broader applications for Monte Carlo methods. The potential is huge.
Definitely opens up possibilities. So here's something for you, the listener, to think about. We've seen how randomness and simulation can crack incredibly tough problems in science, tech, finance. Think about your own world, your interests, or the big challenges out there. Where else could this surprisingly powerful approach harnessing chance be used to find new insights or maybe even solve problems that seem intractable today? Something to chew on.